Chapter 2 is on dimension, rank, and linear transformations. 2.1, we'll talk about independence, specifically what's called linearly independent, and dimension. Some of this, we've already seen the start of the concepts in chapter 1, and this will start to kind of more formalize things. So first, before we get into the definition, let's look at an example. So suppose or let S be a subset of R3, where S is equal to this set. We can see it has three components of each vector, which is R3. But we can label those vectors V1, V2, and V3. Then with a little bit of work, you can see that 0 is equal to negative V1 plus 3V2 plus V3. And so, and I'll show you that too in a second here. So what we can also show really then is if you add that to both sides, you can start with V1. So you can say V1 is equal to 3V2 plus V3. So if you can do that, and then let's just go ahead and write that out. So that's 3 times 0, 1, 2 and then we're going to add V3, which is 1, 0, negative 5. And so you get, let's determine that. So let's just say we didn't know what that is. So if we distribute, we get 0, 3, 6. And you're going to add that to 1, 0, negative 5. And when you do, let me erase that there. When you do, you get 1, 3, 1. 1, 3, 1. Which is, of course, V1, just like I had mentioned, of course. So, I mean, you won't have to guess this. This is just an example to show you that V1 is made up of a linear combination of V2 and V3. We say that this set of vectors is linearly dependent. That's the concept. So we say S is a linearly dependent set of vectors. And sometimes we drop the linearly part and just say dependent. So we can abbreviate and say linearly dependent like that. Or we say the vectors are dependent. And so that has to do with a basis spanning a set and those concepts as well. Because when we talked about a basis, we talked about the only way you can get 0 is if all those coefficients were 0. That is exactly what we're going to mean by linearly independence in a second here. So what you do to check this is the simple way of doing this, and we'll to see if these sets are dependent or not, is you look at this matrix as these are column vectors, V1, V2, V3, like this, and you row reduce. That we've already done, basically. If you get I, then that set formed a basis, right? That was our concept. So if this is true, that is basically equivalent to this, that R1 V1 plus R2 V2 plus R3 V3 is equal to 0, 0 vector that is, and you'd be able to conclude these are all 0. And I'm demonstrating with a 3x3 system in R3. So what you get then for linearly dependence and independence looks like this. And this is something we would have seen before in Calc 3, or multivariable calc. So linearly dependent vectors would be this case here, where W1 and W2 are in the plane, and then this vector is still in the plane because it's a linear combination of the other two. In this case over here, these all would be, so these we would say right now, we haven't defined anything yet, we'd say these are, this would be a dependent set, W1, W2, and then this is dependent, meaning it like depends on 1 and 2, or W1, W2. This set over here, these are not dependent on each other. So to construct W1, it doesn't matter about W3 and W2, W3, meaning they don't depend on them. That's where the terminology comes from. If you take, and here's the span, if you take W2 and W3 and you do the span, you'll get all of that plane. But you will not get anything that comes up like that off the plane. Okay, let's continue. I have another example before I define the 2.1, definition 2.1. So let's look at this one. So like I was saying here, you won't have to guess this sort of thing. We have this process to check it. So that's what I want to do next. So let S equal the set of vectors 1, 2, 0, 1, 5, 1, and -2, -1, 1. So the question is, does S form a basis for R3? Does S form a basis for R3? And I need to point out, basis with an I is singular. And if you put an E right there, that's a plural. So if you do bases, that's plural. So sometimes I'll mix those up because I'm not thinking about that. My apology on that one, but if I mess it up, it's either singular or plural if I accidentally put an E in there. All right, this one we've already done before, but it also has to do with dependence or not. Okay, so what you do is you form, so we'll call this V1, V2, and V3. So you form the matrix, we'll call it A, why not? So A is V1, V2, V3, like this, and then we will reduce it. So it's 1, 2, 0, 1, 5, 1, and -2, -1, 1. Like that. So either now at this stage, go ahead and use your calculators or a computer to row reduce. So row reduce, and you get 1, 0, -3, 0, 1, 1, and then this row zeroes out. And so we would, from chapter 1, conclude that V1, V2, and V3 does not form a basis for R3. So this is basically not equal to the identity matrix, the 3x3 identity matrix. So therefore, S is not a basis, did it again, bases, is not a basis for R3, and we say that those vectors then are linearly dependent. And the vectors, so you don't say the set is dependent. You say it's a dependent set of vectors. So and V1, V2, and V3 are linearly dependent. So that's what you would do above here as well. You would take those three vectors. They're different, right? I was giving, okay, yeah. Same thing would happen here. If you took those three vectors, created this, you will not get I since they're dependent. Okay, I think we're ready then now for the definition. Let me move this up a tick so we can see. So this is definition 2.1. So this is on linearly dependence and independence. So linearly dependent and linear dependence and linear independence. Sorry about that. Okay. And usually we just abbreviate. We say linearly dependent or linearly independent. So let's let the set W1 to W sub k be a set of vectors in Rn. So it would be a set of vectors in Rn. Let R sub I be in R. So these are constants. And then I would range from 1 to k. Not necessary, but I ranges from 1 to k. They are the coefficients of this sum. If R1, W1 plus all the way to RK, WK equals 0, and not all R sub i's equals 0, then the set the set in question, when we're talking about here, then this set is linearly dependent. So then the set W1 to W sub k is linearly dependent. Okay, so then similarly, basically, if the only way to get that sum to be 0 is if all the r's are 0, then they are linearly independent. So that's really the key there. And then forms a basis and all that kind of stuff. So if R1 equals, etc., down to R sub k equals 0, is the only way this sum equals 0, I'll just copy that. If it's the only way that this sum equals 0, then the set. So then this set. Oops, I'm going too fast there. What did I just take? Oh, duplicated it. We'll have to erase that. All right. Okay, then this set is linearly independent. So let's just recap that one. So linearly dependent and independent. It's looking at the sum of vectors. If you can get the sum of those vectors to be 0, and not every single coefficient is 0, then the set is linearly dependent. If the only way to get this to be 0 is that all of those coefficients are 0, then we say the set is linearly independent. Which, of course, has implications for bases and things like that. Okay, let's go ahead. So, and then when you're looking at this form here, so this equation here is basically this product. So this is how we can use matrices to help simplify this stuff. These are all column vectors like this. And then you're multiplying by those r's. So this is just like solving a system, essentially. R1, R2 down to R sub k. And so it's essentially the homogeneous system of what this is. So that's not just 0, right? That's a 0 vector. If you consider it being a column vector, then you can write it in this form. So solving this homogeneous system for unique solutions, or infinite number of solutions, etc., has to do with linearly independent or dependence of those vectors themselves. Okay, let's do one more example. Okay, and then we'll do another video. Okay, so let's let W1 equal the vector 1, 2. We'll just stay in 2 dimensions. And W2 be the vector -1, 0. So linearly dependent or linearly independent, right? So that's the question. So how do you do that? Well, we know how to do this form now. So this is the same thing as really spanning R2, but now we want to look at independence and dependence. So the question is, when you solve this, you put it in the matrix form. So it's 1, 2, -1, 0. And then this is R1, R2, set equal to 0, 0. So we row reduce. Now I'm going to show you that product. You don't have to do this, but you're really just doing this product to see if this system has a non-trivial solution. Okay, so think about that. So if this system has a non-trivial solution, then what is your conclusion? It's LD. So the question is trivial solution or not. So if the only solution is the trivial solution, meaning R1, R2 over 0, then they're linearly independent. If there's another solution where you have different r's, right? That's exactly what it's saying up there, right? Okay, so not all 0. So that's solving that system, basically. It's the same connection. Now, what you do is you just put it in the matrix and solve it. So 1, -1, 0. And now, again, you can use your calculator to just check it, because we'll be doing a lot of these. So when you do this, you get what we're looking for. You get that. So it's row equivalent to that, which means, what does that imply? That implies R1 is 0 and R2 has to be 0. So it is the only trivial, it's the only solution. So there's a unique solution, and it is the trivial solution. So what is our conclusion? Therefore, W1 and W2 are what? That means that they're linearly independent. Okay, so that's what you do. And it could be bigger, but you form the matrix, row reduce. So this, every time I do that, that's row reduction essentially, right? Do you get I? If you do get I, then the vectors are linearly independent. If you get a different solution otherwise, you'd probably get like an infinite number of solutions for homogeneous, then they're linearly dependent. Okay, so that's the concept, and we will start building on that. So this has to do also with do the vectors span? So what would be a good question here? So so another way of writing this we would have seen in chapter 1 is, do vectors W1 and W2 span R2? And the answer would be what? So do these vectors span R2? And the answer basically is yes, they do span R2. Because we showed that with the matrices before, but now we're talking about independence and dependence. And since they're linearly independent, they do span R2. That's how we'll be able to show that. And that's theorem 2.1, which we will do in the next video. Okay.